In today's video, we're diving into the world of software architecture to explore a pattern that's gaining a lot of attention: the modular monolith. You might be familiar with traditional monolithic architectures, those single large codebases. And you've probably heard about microservices, distributed systems made up of many small independent services. The modular monolith sits somewhere in between, aiming to capture some of the benefits of both while avoiding some of their pitfalls. So, what exactly is a modular monolith? At its core, a modular monolith is a single application deployed as one unit, just like a traditional monolith. However, the key difference lies in its internal structure. Instead of a tangled web of code, a modular monolith is organized into independent modules or components with well-defined boundaries. These modules group together related functionalities based on business domains. Think of it like this. Imagine a large house. A traditional monolith would be like one giant room where everything is mixed together. A modular monolith, on the other hand, is like a house with separate rooms: the kitchen, the living room, the bedrooms, each with its own purpose and clear walls, even though they're all under the same roof. Why even consider a modular monolith? The rise of modular monoliths is often seen as a response to some of the challenges encountered with both traditional monoliths and microservices. Traditional monoliths over time can become complex and difficult to understand, maintain, and scale. Changes in one area can unintentionally impact others, and large codebases can lead to slow builds and sluggish IDE performance. Upgrading technologies across the entire monolith can also be a massive and risky undertaking. Microservices, while offering benefits like independent deployment and scaling, introduce their own complexities. These include distributed development challenges, the difficulty of setting service boundaries correctly, increased network overhead, and the complexities of distributed transactions and testing. The infrastructure costs can also be higher. The modular monolith aims to strike a balance. It allows you to define logical boundaries within your system, without the added complexity of physical boundaries inherent in microservices. Several key principles underpin the modular monolith architecture. High cohesion. Each module should group together functionalities that belong to a specific business domain. This means that related code stays together. Low coupling. Modules should be as independent as possible, minimizing dependencies on each other. This makes it easier to modify one module without affecting others. Well-defined public interfaces. Modules communicate with each other through explicitly defined APIs. Internal implementation details are hidden. Accessing code outside of these public APIs should be restricted. Data isolation. Ideally, each module should have its own data storage, or at least separate database schemas, to further reduce coupling and achieve data isolation. Avoid transactions that span across multiple module databases if possible. How do these independent modules talk to each other within the same application? Several approaches exist. Function calls. Overuse can lead to tight coupling if not carefully managed. Some suggest treating these calls as internal API interactions. API calls. Modules can interact through well-defined interfaces, similar to how microservices communicate via APIs, but without the network overhead. Event buses or message queues. Asynchronous communication, using in-memory event buses or message queues, can further decouple modules. When transitioning to microservices, this can make it easier to move to external message brokers. Embracing a modular monolith architecture can bring several advantages. Only a single application needs to be deployed. Improved performance. In-process communication between modules is faster, eliminating network latency and serialization overhead. A single codebase can simplify debugging and the overall development experience, especially in the early stages of a project. Less infrastructure is needed compared to microservices, reducing operational overhead. A well-structured modular monolith provides a clearer path to microservices. Modules can be extracted into separate services gradually as needed. Of course, no architecture is a silver bullet. Modular monoliths also have their trade-offs. Scaling challenges. Since all modules run in the same process, a failure in one module could potentially affect the entire application. However, deploying modules as separate processes for fault isolation is also an option, though it adds complexity. Still a monolith. Despite the modularity, it's still a single potentially large code base, which can present a challenge as the system grows very large. Testing modular monoliths. Because modules might communicate asynchronously, tests may need to account for potential delays. A modular monolith can be a good choice when you anticipate the need for modularity and clear boundaries, but want to avoid the initial complexity of a distributed system. You might want to transition to microservices in the future. You want to improve the organization and maintainability of a growing monolithic application. You have teams that align with specific business domains. The modular monolith architecture offers a compelling alternative in the software architecture landscape. By focusing on internal modularity within a single deployment unit, it aims to provide a sweet spot between the simplicity of monoliths and the flexibility of microservices. It's a pattern worth considering, especially as a way to manage complexity and prepare for potential future evolution of your system.